In this set, applying function notation, we're going to put everything we've learned together. This is an example of a practical problem that uses function notation. You'll notice that instead of saying f of x, it says v of r. What this means, and this is the reason why function notation is so much better to use, is because it tells us that there is a function that gives volume that uses ratio as the variable. If you look at the right-hand side, you can see that the only variable here is radius. Sorry, not ratio, radius. Now we should be able to recognise that this formula is the formula for the volume of a sphere, which we can see, this says volume using radius as the variable. This is an example of a question for applying function notation. It tells us that the volume of the sphere is given by this rule, which you saw also up here, and it asks you to state the practical domain of the function volume, or v, and find the volume when the radius is 10. To answer this question, I'm going to put in the graph of this volume rule. I've used Desmos to do it, but you can use your calculators to do it. Just remember that when you do it, in place of r, you'll need to put x because your calculator works off x. It will make no difference to the final graph, however. Moving down here, looking at this function, this is what we will find out later is called a cubic function. Now the question asks you to state the practical domain. Now this is a real life problem which implies that the volume has to be a positive number. Therefore, the domain should be, or has to be, everything that is bigger than 0 or equal to 0. Oops. Union 0. Alright, so if we had a real world problem, there's no possible way to have a negative volume, which is where the line is to the left of the y-axis. There is no possible way to have a negative volume. The only possible volume we can have can be positive ones. So therefore, this is the practical domain of the function. X is a subset of real positive numbers combined with 0. Remember, if you want to include 0, you have to do this. Otherwise, 0 is not included. The way to write this in set notation would be to start from 0 included and go all the way to infinity excluded. The second half of the problem, listed here, it says and find v at 10, asks us to find the volume when the radius is 10. To do this, we're simply substituting 10 in place of the radius in the question. As I've shown you over here, I've written down v at 10 equals, then the original function, which is 4/3 pi, and in place of r, I've written the value given to us, which was 10. Then I've stepped it down, 10 cubed is 1,000, and then the next step, I've expanded the bracket, and it's become 4,000 times pi divided by 3. Now, I'm going to leave it as that, because as you should know, pi is an irrational number, and as soon as I turn anything with pi into a decimal, I've rounded it off. So this is the most exact answer I can possibly get. Then, being a real world problem, I have to state the units and the fact that it's cubed, which shows volume. Here is an example of another problem. It says that there is a function where the domain is real numbers, the codomain is real numbers, which we can just put to the side and ignore for now, and that the function of x is a times x plus b. It also tells us more information. It says that the function when x equals 1 is equal to 7. What this means is the y value when x equals 1 is 7, and the function when x equals 5 is 19, which means that the y value when x equals 5 is 19. What it's asking us to find is the values of a and b, because these, for us to define this function properly, we need to know what a and b are. We're going to do this using simultaneous equations, but first we need to substitute this information into the function. As you can see here, I've substituted f at 1. We know that the bracketed 1 is where the x is what takes the place of the x, so that sits in place of the x over here. Now, we also knew from the original information that f at 1 equaled 7, so I can change this left-hand side to become 7. We know that a times 1 just equals a, and the b hasn't been affected, so 7 equals a plus b. The second information tells us that the function at x equals 5 is equal to 5 times A, or A5, plus B. I've substituted the left-hand side for what it tells us are equal to, 19, equals 5A plus B. Now I'm going to solve these two simultaneously. I'm going to choose to use the elimination method because I have a singular b in equation 1 and a singular b in equation 2. So if I subtract equation 2 from equation 1, that will leave me with all the a's and no b's. So I've written down the left-hand sides subtract each other equals the two right-hand sides subtract each other. Notice that I have to subtract both 5a and b to ensure that the b's will disappear. This is going to leave us with minus 12 equals minus 4a. We can keep simplifying and divide both sides by minus 4, cancel out minus 4, therefore 3 equals a. From there, it's just a simple matter of substituting that a equals 3 into either of the equations. I'm going to choose to do it in equation 1. 7 equals 3 plus b, minus 3 from both sides, therefore positive 4 equals b. This means that to define the function, we now know the a and b values, and we can say that 3x plus 4 is the function. Notice that I've used the same notation f of x as given in the original, but now I know the a value and the b value. In this question, we've been given some information about a quadratic function f, such that f when x equals 4 equals f when x equals minus 2 equals 0. And the other piece of information is f when x equals 0 is 16. Now we should be able to recognise that if a value equals 0, if the y value is 0, that those are the x-intercepts. Function notation has also told us what the x value is when the y value is 0, and it's positive 4 and minus 2. Now because we're dealing with a quadratic, this means that straight away I can type in my x-intercepts in factorised form, which will be x minus 4 and x plus 2. Alright, now the third piece of information we have to remember is given to us so that we can find out what the a value is, which by default sits out the front of any quadratic until you solve it and find it. Alright, so the third piece of information we're going to use to find out that a value. Now it tells us that f when x equals 0 is 16. So the function is equal to 16 when x equals 0. So we have 0 in place of each x inside the equation. So now I just go through and solve one step at a time for my a value. Minus 8, divide both sides by minus 8. I end up with minus 2 equals a. Now the final step is to ensure that we rewrite the equation defined in function notation. Make sure we look at what it's given us. It says that the function, in the original question it says the function f, so that's the same letters we have to use down here in the answer. And we have the variable of x equals, and we're going to use our a value. Now we can either expand these factors or we can leave them in factorised form. I don't really mind. You'll notice that the book in the example has expanded them. Oops, I'll just make that a bit smaller so I can fit it. It really makes no difference so long as each is the same. If you expanded it incorrectly, then you would get the question wrong. So this is another example of how function notation is so useful for us, because it can tell us literally two pieces of information at the same time, a y value and its corresponding x value, without having to write down two separate pieces.